Hi, this is Mrs. Baisden, and in this screencast we're going to talk about solution stoichiometry, which is section 4.6. So when you do solution stoichiometry, it's very similar to the stoichiometry we've already done. The difference is we can now talk about volumes of substances instead of just grams because we can use molarity as a conversion factor. So if we look at the little chart here, this was what we talked about in the last chapter, going from grams of A to moles of A, moles of B, grams of B. So this little section here was what we have already done. Now, knowing that molarity is the same as moles over liters, we can use that as a conversion to get from moles of one thing to the volume of molarity. You could go from moles of A to moles of B and then to the volume or molarity of B. So it opens up a few more pathways as we're using stoichiometry to solve problems. So let's look at an example of this. Just like before, we're always going to start with the balance equation. So this is how many moles of water form when 25 milliliters of a 0.1 molar nitric acid solution is completely neutralized by NaOH. So what that means is we have HNO3 reacting with NaOH, and this is a double replacement reaction basically. It's also called an acid-base reaction, but you can kind of look at this as a double replacement. We get sodium nitrate and water formed. So HOH, which is the same as water. Then this is already balanced. So what we do with these, notice they give us two pieces of information about the nitric acid. So instead of just saying how many grams of something or how many moles, it tells us a volume and a molarity. So when we start these, we're going to start with the volume. So I'm going to start with the 25 milliliters of HNO3. And then the first thing I have to do is get rid of the milliliters. So 1 liter is 1,000 milliliters. And to save a step here, if you want to go ahead and convert it before you even put it in the conversion equation here, you could do that. Okay, so that takes care of liters. Now, this 1 molar, 0.1 molar is the same as 0.1 moles over 1 liter. So like we said before on the previous page, molarity is moles per liter, so if they give us a molarity, that's the same as saying 0.1 moles of that substance are in 1 liter of that substance. So because it has moles and liters, I can use that as a conversion to get from volume to moles. So I'm going to put my 0.1 moles per 1 liter, and this again is HNO3. Okay, so that allows me to get rid of milliliters, get rid of liters. Now I'm in moles of HNO3. So now I can use my mole ratio from the balanced equation to get from moles of HNO3 to moles of water, which is what this problem is asking for. So there's a 1-to-1 ratio. So 1 mole of H2O for every 1 mole of HNO3. Okay, so at that point, this is now just a stoichiometry problem, so I can multiply across, divide top to bottom. So I end up with 2.50 times 10 to the negative third moles of water. Okay, now you could take this to grams from here, or you could actually take it back to molarity, which we'll look at a couple examples of those in just a minute. This is in scientific notation. It would not have to be. You could leave it in regular form, but for this particular one, I'm going to put it in scientific notation. Okay, so here's a couple other examples. So this first one is the one we just did. So we're going to skip this first one. The second one says how many moles of NaOH are needed to neutralize 20 milliliters of 0.15 molar sulfuric acid solution. So for this one, if you look back at what we did before, maybe stop this for a second and see how far you can get with this one on your own. Now I'm going to go ahead and write the equation above since I'm running out of room here. So just like always, start with the balance equation. So we're reacting H2SO4 with NaOH. And again, this is an acid-base reaction, which is similar to a double replacement. I'm going to get Na2SO4 plus H2O. This one I do need to balance, so I'm going to balance it that way. And then, just like before, I'm going to start with my volume. So I have 20 milliliters of H2SO4. I need to get rid of the milliliters, so 1 liter is 1,000 milliliters. Then, like before, I'm going to use my molarity to convert from liters to moles. So I 0.15 moles of H2SO4 per 1 liter, because again, that big M is equal to moles over liters. And then now I can go to my balance equation and look at my ratio between H2SO4 and NaOH, which is what it's asking me for. So it's a 2-to-1 ratio, so there's 2 moles of NaOH per 1 mole of H2SO4. Okay, so that equals 6.00 times 10 to the negative third moles of NaOH. And notice we're still taking into consideration our sig figs here. So I have 3 sig figs here, 3 here, so I'm going to leave my answer as 3 sig figs. And again, you could leave it in standard form. You wouldn't have to leave it in scientific notation, but sometimes the scientific notation makes the sig fig stuff easier. Okay, the next thing we want to look at is what is a titration. So this should look familiar since we did one of these in class already. And what a titration does is it takes a known solution and it allows you to figure out the concentration of an unknown solution. So if we look at our setup here, again, this should be similar to what we did before. We've got a solution here that goes into our flask at the bottom. We have a known volume, but we have an unknown molarity. So this is our volume of this one, we know, is 20 milliliters. But for this one, the molarity or the concentration, we don't know. For our standard NaOH solution, this one we would know the molarity of, and we'd see how much of that solution is needed to change this solution at the bottom to the endpoint. Now this particular one had an indicator. The one we did in class, we used that oxidation state change as our indicator. So like we just said, we have a substance of known concentration. It's used to react with a substance of unknown concentration. Okay, so when you end up with equivalent quantities of the two solutions, then we are at what's called the equivalence point. And then we stop at the equivalence point, and that's when we take our readings, and then we can do our calculation from there. We use an indicator, and the indicator could either be something we add, which we'll do later on when we do acid-base titrations, or it could be a change in oxidation state like the lab we used. When you have an indicator, whether it's an acid-base indicator or an oxidation reduction indicator like we used, they're going to change color at what's called the endpoint. So that's how you know that the reaction has taken place to the point where you have equal amounts, and then you can use the stoichiometry to figure out the amounts. When you pick an indicator, you're going to pick one that changes or corresponds to the equivalence point of the titration. So this particular one, we were using an oxidation state change. If we're doing an acid-base reaction, then we would pick an indicator that changed at the appropriate pH, which we'll talk more about later on. Okay, so here's another picture example. So again, this should look familiar because you did this. You continue to add your known solution until you get a nice, very slight indicator change. All right, so let's look at a couple examples of this one. This one says, how many grams of chloride ions are in a sample of water? If you have 20.2 milliliters of 0.1 molar silver ion are required to react with all the chloride in the sample. So this one, because this is a reaction between ions here, we have silver and chlorine, and that gives us silver chloride. So for this particular one, we're looking for how many grams of chloride ions are in this sample. So just like before, we're going to start with our known volume and our known molarity. So I have 20.2 milliliters of silver, and we're still going to look at the relationship between those two. So first step is to get rid of that milliliters. Then I'm going to use the molarity to convert to liters. So I have to moles. 0.1 moles of silver for every 1 liter. Now I can go to my stoichiometry, so this is a 1-to-1. So I have 1 mole Cl minus for every 1 mole of silver. So very similar to what we did before. This one, though, we're actually going to go all the way to grams, so I can use a molar mass, just like I did before. So 1 mole of Cl minus. I'm going to look at the molar mass on the periodic table for chlorine, which is 35.45 grams. Okay, so then what this tells me is I have 7.16 times 10 to the negative 2 grams of Cl minus. Okay, now this particular one, we could also calculate percent, just like you did in the hydrogen peroxide lab. So if I know that the mass is 10 grams, so that would have to be given to you, but let's say the mass of the sample was 10 grams, then we could figure out what percent chlorine or chloride ions did it contain. So then we would take our 7.16 times 10 to the negative 2 grams divided by 10 grams, and then we'd multiply by 100 to get our percent. So that would tell us this particular sample had a 0.716% chlorine ion percentage. So this type of analysis could be used when you're testing to see what substances are present in maybe a drinking water source, so they can titrate with a known substance, and then that'll give you a percent for that particular ion or whatever the substance is you're looking for. Okay, so this was a problem we just completed. And then I'm going to skip over this one. We can do this example in class if you want to see another example, but I'm going to do one more, this very last one here. If you look in your notes, this says that one commercial method for peeling potatoes is soaking them in sodium hydroxide. That does not sound good at all. But that is one way that they can do, one method they can use to peel potatoes. So they then spray the peel off after it's reacted with the NaOH. When they do this, they have to take samples and make sure that that concentration is in the correct range. So the concentration this particular place would be looking for is in a range of 3 to 6. So it tells you here that in one of these analyses, 45.7 milliliters of 0.5 more H2SO4 is required to neutralize a 20 milliliter sample of the solution. So we want to know the concentration. Again, this is just another example, so if you're good with these, you can stop at this point. But this particular one, we're also going to calculate the molarity. So you may want to watch this one because it does have one extra step at the end that we haven't done yet. So just like before, I'm going to start with my molarity, or my volume, 45.7 milliliters of H2SO4. And I would need a balance equation. We already did this balance equation on a previous example, so I'll write it here in just a second. Actually, let's stop and do that now. So it's H2SO4 plus 2 NaOH gives me Na2SO4 plus 2 H2O. So again, you'd have to start with that, but we did that reaction a minute ago, so we're just copying it over. Then we're going to use a 0.5 moles per 1 liter of H2SO4. Then we're going to use my mole ratio between sodium hydroxide and H2SO4. So 2 moles NaOH for every 1 mole of H2SO4. So that gives me 0.0457 moles of NaOH. Okay, now the last step here is they would have to give you one more piece of information here. They would have to tell you how big the sample was. So if the sample of NaOH was 20 milliliters, we can now figure out the molarity, because we know the molarity is moles per liter. Moles I just figured out, so 0.0457 moles per 20 milliliters, which I'm going to change to liters, 0.020 liters. So if I do this calculation then, I end up with 2.28. I'm going to write it up here. 2.28 moles NaOH. which for them, if they require 3 to 6 range, this would be a little bit low, so they'd have to adjust the concentration.